Welcome back to Data Dialogues, where we explore cutting-edge research in statistics and machine learning. Today, we're diving into a fascinating paper about making hidden Markov models work for massive data sets. We're joined by Dr. Sarah Statz, an expert in statistical machine learning. Welcome, Sarah.
Thanks for having me. I'm excited to discuss this paper.
So, Sarah, can you start by giving us a quick overview of what hidden Markov models are and why they're important?
Certainly. Hidden Markov models, or HMMs, are a powerful tool for analyzing sequential data. They're used in speech recognition, genomics, finance, anywhere you have data that unfolds over time, and you suspect there are underlying hidden states influencing what you observe.
That sounds really useful, but I'm guessing there's a catch?
You're right. The catch is that traditional methods for working with HMMs don't scale well to very large data sets. As the amount of data grows, the computational cost becomes prohibitive.
And that's where this paper comes in, right?
Exactly. The authors have developed a new algorithm that allows us to apply HMMs to massive sequences of data. We're talking millions or even billions of data points.
Wow, that's impressive. How does it work?
The key idea is to use something called Stochastic Gradient Markov Chain Monte Carlo, or MCMC for short. It's a way of estimating the model parameters using only small subsequences of the data at a time, rather than the whole data set at once.
That sounds clever. But doesn't breaking up the sequence lose important information?
That's a great question. You're absolutely right that we need to be careful about breaking dependencies. The authors use two key techniques to address this. First, they use buffers around each subsequence to capture some of the context. Second, they space out the subsequences they use based on the mixing time of the Markov chain to ensure they're approximately independent.
Fascinating. Can you explain what you mean by mixing time?
Sure. The mixing time is essentially how long it takes for the Markov chain to forget where it started. By waiting this long between subsequences, we can treat them as almost independent, which is crucial for the statistical properties of the algorithm.
I see. So what are the main advantages of this new approach?
There are several key benefits. First, it's much faster than traditional methods for large datasets. Second, it can handle non-conjugate models, which gives us more flexibility in how we specify the model. And third, it asymptotically samples from the true posterior distribution, which means we're getting accurate uncertainty estimates.
That sounds really powerful. Are there any limitations or challenges?
As with any approximate method, there are trade-offs. The algorithm introduces some approximation error, although the authors provide theoretical guarantees on its behavior. Also, choosing the right buffer size and subsequence length requires some care.
Got it. So what kind of impact do you think this work will have?
I think it could be quite significant. There are many fields where we have massive sequential datasets that are currently challenging to analyze with HMMs. This method could open up new possibilities in areas like genomics, finance, or analyzing sensor data from IoT devices.
Fascinating stuff, Sarah. Thank you so much for breaking this down for us.
My pleasure. It's always exciting to see new methods that push the boundaries of what's computationally feasible.
And that's all we have time for today on Data Dialogues. Thanks for tuning in, and we'll see you next time.